Good day, everyone. We have successfully completed our assignment, subject code ECT 1026, Field Theory, Trimester 1, 2020 and 2021. These are our group members: Dominic Ong Chi Yong, Kavi Alagan Annalagi Ravi Sandran, and also myself, Manoj Nair Annalagi R. Madhu Nair. Well, first of all, let's see what is magnet. Magnet is an object that attracts iron and few other metals. Magnet also attracts steel because it contains iron. There are different shapes of magnets, like bars, some are U-shapes and some are thin and flat. There are always two poles in a magnet, which is North Pole and South Pole. Magnetic poles are always in pairs. You will never find a magnet that has only a North Pole or only a South Pole. The region around the magnet is called as magnetic field. Next, the right-hand grip rule. The right-hand grip rule is to determine the magnetic force, current and magnetic field. The thumb is to show the current is going upwards, and the fingers are turned around to show the magnetic field. These are the formulas that we have used throughout this assignment. First, to find the magnetic field strength. Next, to find the magnetic flux density. Next, to find the magnetic flux. And to find the magnetic field due to a long straight current carrying wire. And also to find the EMF. Now, let's have a look on the assignment questions. Question 1. A coil of 300 turns is wound uniformly over an air ring having a mean circumference of 400 mm and a uniform cross-sectional area of 500 mm square. If the current through the coil is 4 ampere, calculate the magnetic field strength, the magnetic flux density, and also the magnetic flux.
Hi, I'm Manoj Nair. Today I'm going to solve question 1a, which is to find the magnetic field strength. So in the question is given that N equals to 300 turns, circumference is given that 400 millimeter, and cross-sectional area is given 500 millimeter square, and current is given 4 ampere. So we have to change 400 mm to m and 500 mm to m square. So 400 divided by 1000 is equals to 0.4 m, and 500 divided by 1000 equals to 0.5, and we have to divide it by 1000 again to get m square, which is 0.0005 meter square. So to find the magnetic field strength, the formula given is H equals to Ni over L. So N is 300 turns, I is 4 ampere, and L is 0.4 meter. So let's calculate that. 300 times by 4 is equal to 1200, and divide by 0.4 is 3000 ampere per meter. This is the final answer for question 1a. Thank you.
My name is Dominic. Now I would like to explain question 1b and c. Question 1b wants us to find the magnetic flux density B. From calculation of question 1a, we know that magnetic field strength H is equals to 3000 ampere per meter, and constant mu naught is equals to 4 pi times 10 to the power of negative 7 Tesla meter per ampere. The formula of magnetic flux density B is equals to the constant mu naught times the magnetic field strength H, and is equals to 4 pi times 10 to the power of negative 7 Tesla meter per ampere times 3000 ampere per meter. Ampere cancel, meter and meter cancel, and is equal, the magnetic flux density is equals to 3.77 times 10 to the power of negative 3 Tesla. Question 1c wants us to find the total magnetic flux. From question 1b, we know that the magnetic flux density B is equals to 3.77 times 10 to the power of negative 3 Tesla, and the cross-sectional area given in the question is equals to 500 millimeter square. To convert to meter square, we need to divide it by 1000 square, and it is equals to 0.0005 meters square. The formula of the total magnetic flux is equals to magnetic flux density times the cross-sectional area, which is equals to 3.77 times 10 to the power of negative 3 Tesla times 0.0005 meters square, and it is equals to 1.885 times 10 to the power of negative 6 Weber. Now I would like to pass the presentation to Kavialagan, my groupmate, to explain question 2.
Now, let's go into question 2. Figure 1 below shows a wire and a metal rod. If the metal rod moves with constant velocity of 5 meter per second, find V12. This is the figure given.
Good day, I am Kavialagan and I am going to solve question 2 referring to figure 1. In figure 1, they have given us that current I is equals to 10 ampere and R is 10 centimeter, which is 0.1 meter. I have converted it, and the length of metal rod is 30 centimeter and I have converted it to 0.3 meter. And the velocity is a constant velocity where it is 5 meter per second and it moves in direction Y. The current I induces a magnetic field which is given by the formula mu naught I over 2 pi R. Now, in the question, they have asked us to find V12. V12 is equals to VEMF, which is given by the formula integrate B times V times dr. Now I'm going to start our calculation. Now I'm going to substitute B. B is mu naught I over 2 pi R times V. Next, I'm going to separate the R from the formula mu naught I over 2 pi times V times 1 over R. Now I'm going to move the integration sign in front of 1 over R. Okay, now I'm going to substitute the value for mu naught I over 2 pi. Mu naught is a constant which is 4 pi times 10 to the power of negative 7, and I is the current which is 10 ampere, over 2 pi times the velocity, which is 5 meter per second, now we get 1 times 10 to the power of negative 5 times by integrate 1 over r. dr. Now, to find the limits of 1 over r, the upper limit would be r plus L metal rod, which is equals to 0.4 meter, and the lower limit would be 0.1 meter. Therefore, 1 times 10 to the power of negative 5 times the integration 0.4 and 0.1 1 over r dr. Now I'm going to integrate 1 over r. When I integrate 1 over r, I got ln r with the limits 0.4, 0.1. Now I'm going to solve for ln r. And the value I got is 1.386. I'm going to take 3 decimal places. 1.386. Now we're going to times this together. And the final answer is 1.386 times 10 to the power of negative 5 volt. The answer for V12 is 1.386 times 10 to the power of negative 5 volt, which is V12. Thank you.
In conclusion, I would like to thank my teammates and also my lecturer, and not forgetting my viewers as well. Thank you.